We are continuing now with these review problems. You can see on the screen, we're ready for problem 39. This is a new kind of problem, so I'll take a few minutes to give a quick review of what we're doing. Then we work out the problem. So problem 39 says, find an equation for the line that is tangent to the curve y equals 2x cubed minus 8x at the point -2, 0. So now we're talking about, we've got a function here, an equation, and we're trying to find the equation of the tangent line at this point on the function or on the equation. So let me describe what's going on. I've already started a little description here. So let me go through what I've started with. Here I just drew a random graph, and I decided, okay, at the point where x is 4 and y is 2 on the graph, I'm going to draw my tangent line. And what I really want is the equation of this tangent line. Now, normally when we go and try and determine the equation of a straight line, we use the slope-intercept equation. And this is what we're looking for. We're looking for the equation of this tangent line. But for this kind of problem, the slope-intercept equation is not the best way to solve this problem. There's another equation that you may recall learning about when you were learning about linear equations and graphing, and that's called the point-slope equation. For these kinds of problems, the point-slope equation is definitely the easiest way to solve these kinds of problems. Here's the point-slope equation. Y minus y1 equals m times x minus x1. The reason it's called the point-slope equation is because if you have a point on your line, and if you know the slope of the line, then with that information, you can come up with the equation of the line. So here's the equation. Your point is x1, y1. So whatever point you're given, you plug in x1 and y1, and then you plug in the slope of the line for m, and at this point, then you have everything you need to find the equation of the line. So for this kind of problem, where we're trying to find the equation of this tangent line, we need a point on this line, and we need to know the slope of this line. Well, this tangent line, we know a point right here, the point at which the line touches the graph. We know that point 4, 2. Now I need the slope of this line, but once again, the slope of this line is actually the same as the slope of the curve at that point, right? And that's the whole idea of what we've been talking about with the first derivative. Knowing the first derivative of our graph, of our curve, of our function is going to allow us to find the slope at this point. So here's the deal. To summarize, I'm looking for the equation of this line. I've decided if I know a point on the line and the slope of the line, I can determine the equation. Well, I know the point. Matter of fact, they give me the point. That point is both part of the line and part of the curve or the graph. But secondly, I need to find the slope. How do I find the slope of this line? Well, the slope of this line is the same as the slope of the graph of the function at that point. And we have a way now to determine the slope of this graph. So to find the slope, use the first derivative of the graph. So I'm going to determine the first derivative of the function. And in our case, since I'm looking when x is 4, I plug in x equals 4 into my equation for the first derivative, and that gives me the slope of the graph at that point and the slope of my line. So now I know the slope of my line. I know a point on the line, and I can plug it into this equation and get the answer. So based upon that, let me go back and write down the exact details of the problem we were given. So for this problem 39, let me write it down, then we can work it out. The function or the curve or the equation is y equals 2x cubed minus 8x. The point we're looking at, where we want to look at the tangent line, is -2, 0. And we're supposed to find the equation of the tangent line. So here we go. Once again, the point slope equation is y minus y1 equals m times x minus x1. This right here is my point. I can go ahead and plug that in. Y minus 0 equals m, x minus a -2. Of course, when you subtract a negative, it's positive. So really, this simplifies down to y equals m times x plus 2. So once again, now, if I can determine the slope, then I'm done and I've got my equation. So once again, just to say it again, the slope of my line is the same as the slope of this curve of this graph at that point. So I'm going to go ahead, I'm going to take the first derivative of my function, and it's going to be 6x squared minus 8. So you remember what we've been taught, the first derivative of a function of a graph really represents the slope at every point, every place on that graph. Well, I specifically want to find the slope when x is -2. So I simply plug in -2 into my first derivative, or I could think of it as my slope equation. So this is 6 times 4. So that says actually the slope of the curve at x equals -2 is 16, which is also the slope of the tangent line at x equals -2. So my slope is 16, so I plug this into here. Now I think, I don't know, maybe you can enter it in my math lab like this, but normally I go ahead and multiply it out, and that should be the equation of the tangent line. So let's go see. 16x plus 32. Notice here they say the equation is y equals. So I just type in the equation part. And thankfully that is correct. Okay, here's a similar kind of problem, but with a little twist. So number 40 says, for the function, find the points on the graph at which the tangent line is horizontal. So here's an equation, here's your graph, here's your function. And they're trying to figure out the points on this graph where the tangent line is horizontal. So I'm going to write down the information for this problem, and then I'm going to talk about it, and then we're going to solve it. So let me go and write it down so I don't have to keep going back and forth. So our equation is y equals x squared minus 8. And we're looking for the points where tangent lines are horizontal. So here's the problem, but let me describe what we're actually doing. So once again, easiest way is just to draw some kind of a random sort of graph. And what they're saying is, we could draw a bunch of tangent lines, right, on this graph. But they're saying, go find the point on this graph where the tangent line is horizontal. Obviously, that's going to be right up here at the top. At the top here, if we find where it's going to be the maximum point, the highest point. So really, this point here is what we're trying to find. Now, how do we go about finding out that point on the graph, the point at which the tangent line is horizontal? Well, in this case, you sort of work backwards because hopefully you remember anytime you have a perfectly horizontal line, you know what the slope is of a perfectly horizontal line? The slope is 0. Now, what I'm going to do is, if I find the first derivative of my graph of my function, it really equals the slope of every point on this graph. And you know what I want for this problem? I want to find the point on this graph where the slope equals 0. Because wherever the slope equals 0, then the tangent line at that point would also have a slope of 0. So I go along here, you notice the slope at all these points, like these are all positive slopes. And the slopes get smaller and smaller. And then when you get to the very top of this curve, at this point, the slope is actually 0. And then as you keep going, all of a sudden you have negative slopes. So here's what I'm going to do for this problem. Basically, I'm going to solve this equation. I'm going to take my function or my equation, going to take the first derivative and then set the first derivative equal to 0. And I'm going to solve, I could have said solve for x. And when I solve this equation right here, those values of x will be the point at which the slope is 0. So based upon that, now I'm ready to solve this problem. So once again, in a nutshell, to find the points where the tangent line are horizontal, we're going to solve this equation. Where is the first derivative equal to 0? First derivative here is going to be 2x. That's it. The negative 8 is 0. So the first derivative is 2x. I'm going to set that equal to 0. Now, if I solve this equation, which means get x by itself, divide both sides by 2. And what this is saying now, the tangent line is horizontal, which means the slope is 0 when x equals 0. Now, this is the x. When I'm looking for a point, I need x and y. So I know the x is 0. How do I find the y? I plug 0 back into my original equation. And I plug in 0 in for x. Y is negative 8. So this is the point on this equation, on this function, where the slope is 0, which means the slope of the tangent line is 0. So let's enter this answer and see if that's correct. So I'm saying 0, negative 8. So I'm pretty sure you probably need to put these in parentheses like, because it says type an ordered pair. There's actually only one point where this happens, and that is the correct answer. Now here, problem 41, for what point on the curve y equals 2x squared plus 8 is the slope of the tangent equal to 28? The problem we just did, we set the slope of the tangent line equal to 0 because that's what a horizontal line is. Now they're saying set the slope equal to 28 and find the point on the curve where the slope is 28. All right, we can do that. And we're going to write down this information and we can work it out. So this is problem 41. So the curve is y equals 2x squared plus 8x. And we're looking for the points where the slope is going to be 28. So basically, in this case, we're going to solve y dx equals 28. I'm going to take the first derivative, set it equal to 28, and solve for x. So the first derivative is 4x plus 8. And I'm going to set it equal to 28. And I'm going to solve this equation for x. Subtract 8 from both sides. Divide both sides by 4. So there's the x value of the point where the slope is 28. But once again, a point has both an x and a y. So if the x is 5, what's the y going to be? I have to plug 5 back into the original equation to determine y. So it's going to be y times 5 squared plus 8 times 5. This is going to be a pretty big number. 2 times 25 plus 40. That's 50 plus 40. It looks like 90. So it looks like the point at which the slope equals 28 is 590. All right. Okay, this looks like a little bit like a story problem kind of deal. In T years, the population of a certain city grows from 300,000 to a size P given by this equation. Find the growth rate, find the population after 20 years, find the growth rate. All right, so now we're taking some of the principles we've learned and sort of applying it to a story problem. So now our variables are going to be P, which is the population, and T, which is the number of years. We've got this equation, and the first thing they ask for is the growth rate, and they even give you the PDT, so it's pretty clear the growth rate is going to be the derivative of this equation. And then they ask us a bunch of questions. So let me write down this equation. This is problem 42. So we have P of T equals 300,000 plus 3,000 T squared. Part A is pretty straightforward. They're asking for the derivative. Part B, when they say find the population after year 20, I'm going to write it here. You'll see it in a minute. What that really means is they want to know what P of 20 is. C, the growth rate after 20 years. Once again, you'll see this in a minute. And then D is one of those explain the meaning. All right. So here's what they're asking us, what I've written down. So P is the population, the number of people. T is the number of years. So this basically is an equation that sort of tells you, okay, you choose how many years have passed, and we can tell you the population. You plug in the number of years into this equation, and we'll give you the population. Here, what they're first wanting to know is what they call the growth rate, which is the first derivative. So I'm going to take the first derivative of this equation with respect to T. So this is a constant, so it's 0. So you have 3,000 T squared, so the 2 comes down here. The PDT should be 6,000 T. Now the second part of the question says, what's the population after 20 years? This, you go back and use the original equation and simply put in 20 for T. So you have 300,000. And you can see 300,000 is the original population, right? Because if you put a 0 in for T, which means times 0, you have 300,000. So you start with 300,000. And then as the years pass by, the population grows. So we're going to say, what is the population after 20 years? 300,000 plus 3,000 times t squared, which in this case is 20. So this is where you grab your calculator. So 20 squared times 3,000 is like, wow, 1.2 million plus the city's growing pretty fast. In 20 years, it's gone from 300,000 to 1.5 million. Now this next part says, what's the growth rate when t equals 20? So this growth rate is not the same. The growth rate is changing, and they're saying, okay, how are things growing after 20 years? So you simply take your derivative up here and you plug in 20 for t. Now, I'm going to confirm this on my calculator. I'm going to try to do this in my head. So the growth rate is 120,000. So these are the numbers, and we'll see what D is all about. So the PDT, I said, is 6,000 T. And then the population after 20 years, we said, is 1.5 million. So I got to put 1. And the growth rate at t equals 20, we said, is 120,000. Now, D is probably going to be some kind of multiple choice. What's the meaning of the answer to part C? So part C is asking the growth rate. So like I said a minute ago, that means after 20 years, if you look at that point in time, how is the population growing at that point in time? Population growth is not staying the same. It's changing. So right at that point in time, what's the population growth? 120,000. So it's going to be C. The growth rate tells the rate at which the population is growing at time t equals 20. That's what I was saying. All right, let's see what else we have before we start the next video. All right, now's a good time for a break, because this next problem, now we're just going to do some more sort of conventional straight math problems, or we're going to find derivatives. So let's take a break now, and we'll start the next video with problem 43, where we actually start taking some derivatives.